TUBS-IRMB. Digital India. Educated India.
So then welcome to the 11th GIAN lecture on high fidelity Lattice Boltzmann methods, and today we are actually entering one of the important high fidelity parts, which is the grid refinement. So far we always said that the Lattice Boltzmann method uses Cartesian grids. This is grids with constant resolution, which for fluid mechanics is of course a problem. Now, in the last 10 years or so, a lot of unstructured Lattice Boltzmann methods came into being. But we shall not forget that potentially this Cartesian grid thing that looks like a disadvantage of the Lattice Boltzmann method is actually an advantage of the method compared to other methods. It seems to be a little bit rigid, yeah. So you cannot easily change it. But then on the other side, this also simplifies your algorithm a lot. So you do not need to save, element equations for each and every element in your system. So the different elements or control volumes or whatever you have there, they do not need to know how big they are because they all have the same size. Yeah. So in essence, this simplifies the method a lot, and this allows us to spend more degrees of freedom doing actually more work than would be possible with the same amount of work, of effort, done in, for example, a control volume method where you have complete freedom of how to place these elements. So actually, these Cartesian grids are a big advantage of the Lattice Boltzmann method in practical terms, even though people may disagree with this. So it is both an advantage and disadvantage, yeah, because still you need to resolve something like boundary layers. And this is in particular a problem for external flows. So in internal flows, such like flow through pipes, yeah, engines or so on, they you actually get along with a really Cartesian grid with constant resolution quite well. But once you go to external flows, and this is actually where Lattice Boltzmann historically was used the most. So the historical application of the Lattice Boltzmann method is actually computing the drag force on cars. Yeah. So there's a company called EXA. They have since the 1990s selling this Lattice Boltzmann solver power flow. Yeah, so and this was sold to the automotive industry, and for a very long time this was actually the only software that was able to actually calculate from first principles the drag force on vehicles. And so most of the automotive industry during the 1990s and the 2000 years, they were relying on this particular software. And now if you want to calculate the drag on a car, what you're going to do is I've drawn this in the wrong way, so you would spend more space after the car than before the car, obviously. Yeah. They put this into a wind channel, a virtual wind channel, and then they don't actually need a lot of resolution up here, but you have to capture somehow the boundary layer, which means you have you will have to get a finer grid here and potentially an even finer grid right at the boundary, meaning you would like to have a high resolution close to the surface. And the reason for this, of course, is that dissipation, so lots of the dynamics in the flow, is concentrated in the boundary layer. So you either have a very good boundary equation. Boundary equations are difficult actually to derive, yeah, so they can make a lot of mistakes. So you either have a very good boundary equation or you have a lot of resolution close to the boundary, or in practice actually you need both, yeah, because you neither of the two is usually sufficient. So you have to have some specific boundary condition that mimics your boundary layer, and you need a high resolution on the surface, whereas there can be very little dynamics far away from the boundary, far from, and so in particular in front of the vehicle there is very little dynamic usually, right? So here, you still need this mesh, yeah, because there is some dynamics that you have to capture, yeah, but the requirements on the resolution are very low. This means you would like to spend there only low resolution, yeah, obviously in order to save money, because money is always a problem. So the way this has been done like 30 years ago, so because as I said, the software was in use for solving exactly this kind of problems 30 years ago, is they used volumetric grid refinement, yeah? Say this was popular in the 1990s. There's actually a patent on this from this company. So how did this work? Let us look at our Cartesian grid. Trying to draw a Cartesian grid here. It's like this. Okay, I'm going to do this pretty often today. So say this is a coarse mesh. Now, because they came from a world that was thinking in control volumes, what they did is they defined the surroundings of one of these nodes as a cell, and in this here, this would be a coarse lattice cell. Now this coarse lattice cell could then be split up into fine cells. And this was done by the algorithm that they called in their patent explosion. So the good thing is you can just read the patent. I mean, you can use this method nowadays because the patent is 30 years old, so it's no longer valid. Okay, so you have your, say, we are in 2 dimensions. Of course, you simulate cars in 3 dimensions, but for the simplicity, let's just assume this here. So we do an explosion. This explosion means we have our populations here, and I'm drawing ugly today. And you simply split this up into, say, going from coarse to fine. What you do is this Fij fine simply is Fij coarse divided by 4. Okay, divided by 4 because I've drawn it in 2D. So obviously, if you do, when you're doing this in 3D, you would divide it by 8. So they were actually very stringent on mass conservation. Yeah. So they would say, okay, we have to distribute the mass that is in this one cell over 4 other cells, and they did this very, very simply by taking each of the different directions and simply split this into 4. So these new 4 are in 3 dimensions 8 nodes. Yeah, they would all have the same populations or the same distributions. Yeah, because they are simply split up. So the opposite of explosion is actually implosion, but they called it collapse. So collapse is you take these 4, or in 3 dimensions 8 cells, and you move them into now 1 cell. So this is now fine and is going to coarse. So an Fij coarse will then simply be the sum of n equals to 1, 2, 3, to 4 of Fij fine. So they will simply sum them up. Okay, so this is the end. Yes, okay, so there's 1, 2, 3, 4, yeah? N equal to 1, 2, 3, 4. And this would then be combined with acoustic scaling. I mean, if you do it this way, you have to use acoustic scaling. Delta x by delta t is assumed to be constant. So delta x coarse would be 2 times delta x fine, and delta t fine is equal to 2 delta t, coarse, will be delta t coarse is equal to 2 delta t fine. So this is acoustic scale. Okay, so pretty simple. Yeah, so you split them up, you collapse them together. So this is how it was done. Question. So I told you acoustic scaling is not, we don't have convergence in acoustic scaling, so why do we use acoustic scaling? I mean, one thing, of course, is important. When you do grid refinement, you want to reduce the numerical error. Yeah. So what you can do with this, you can reduce the error in space with this. what you cannot do is you cannot reduce Galilean invariance error. So you cannot reduce errors in the velocity because the velocity is here constant, is not dependent on the resolution. Yeah? Therefore, the Mach error will not get smaller with finite grids in this setup. Okay? So, but why anyway we use acoustic scaling? So you may have different opinions about this. So some people say acoustic scaling is more efficient, yeah, because you have to use only two time steps on the fine grid instead of 4. Yeah. Now you can turn this argument around and say, actually, I don't want to refine my grid. I want to coarsen my grid, and when I coarsen my grid, I get longer time steps on the coarse grid. So this argument is somewhat strange because you could put it in favor for acoustic scaling and in disfavor for acoustic scaling, if you will. But there is a physical reason why we want to have this acoustic scaling, and this is related to the Snell-Descartes law. So around the world, always people, and in particular in Europe, maybe it's also here, but with other people, everybody, so there's always an argument who invented what. Usually back in the days, somebody invented it here and somebody invented it there, and they did not talk to each other. So there is French people who discovered this, and there's English people who discovered this, and wherever you are coming from, yeah, you either take the French name for it, or you take the English name for it, Snell or Descartes. And this is related to the transition of waves in different media where they have different speeds. Yeah, so you may have heard this, right? How do you call it? Because Snell's law. Okay, so you were influenced by the British. Have you ever been somehow influenced by the British? Maybe. Okay, I'm trying to make a sketch here. Yeah, maybe the sketch is not very good, but say we have one medium here, and say this medium here we have one grid here, and this grid, say, has a high resolution, okay? So this is connected to another grid that has a coarse resolution. And suppose we use diffusive scaling. Now let's say there is a wave coming, and the wave has a wave vector, and this wave does not come completely normal, but this wave comes with an angle here, right? So that you could say that there is an angle, say theta 1. Then because we use diffusive scaling, we have on this side delta x fine is delta x cos half, and delta t fine is delta t cos a quarter. So now this means there are different speed of sound in these two domains, and if there's a different speed of sound, you actually get a diffraction here with theta 2, and according to Snell's law, there is this relationship that the sine of theta 1 divided by the sine of theta 2 is equal to the speed of sound in the fine grid divided by the speed of sound in the coarse grid. Yeah, you may have heard this. Yeah, So for example, there's also the reason why you get reflection. So I see reflection in this class here, yeah, because there is a difference in speed of light in between the air and the glass. Yeah? And actually this accounts for, if I'm not mistaken, for 4% of the light being reflected in normal, under normal conditions. That 4% of the light is reflected from a window. So only 96% is actually getting through, due to the difference in speed of light. And the same thing is true for the speed of sound. So since these they have a difference of 2, what you have is that these signs are actually the difference is like 1/2. And now, if you remember, if you have a low, if phi is small, then sine phi is close to phi. So almost the angle will be double, right? In this case. So now if you use instead acoustic scaling, now I mean you see what this. I mean, it's easy to see what this means. You have delta x cos, delta x fine is delta x cos half, and delta t fine is delta t cos half, and now say you have this high resolution thing here. And again, you have the cos resolution there. Then you have the advantage, because the speeds of sound are the same, that this angle phi 1 is equal to this angle phi 2, because, of course, you get now I don't have any space here anymore, the sine of phi 1 divided by sine of phi 2 is Cs fine divided by Cs cos, and because they are the same. So we get the same angle, yeah? Meaning that okay, give some more space here. If we use acoustic scaling at grid interfaces, this avoids reflections. I mean, it avoids reflections 99%, 99 point something percent. If you look very detailed, then avoiding reflections completely altogether for other reasons other than the Snell's law is kind of difficult, in particular if you have very turbulent flow. Yeah, but 99% of the reflection, or more than 99% of the reflection, is suppressed by this, which is different from if you use a different kind of scaling. So, however, as we have learned, acoustic scaling requires a rescaling of the viscosity, and by so doing, it also requires a rescaling of the non-equilibrium part of the populations. So first of relaxation rates. And non-GIP equilibrium populations. Okay, so how does the relaxation rate rescaling look like? So viscosity is supposed to be theta 1 over omega minus 1/2 into delta x squared divided by delta t. So if now viscosity is supposed to be the same, physically the same on all the crits, then we have theta 1 over omega cos minus 1/2 delta x cos squared by delta t. Cos is equal to theta 1 over omega fine minus 1/2 delta x fine squared divided by delta t fine. Now you can eliminate stuff and solve this. For example, say we are given omega cos, then we can solve this for omega fine, or 1 over omega fine, to make it easier to write down. And this turns out to be delta x cos squared divided by delta t cos times delta t fine divided by delta x fine square. So all of this into 1 over omega cos minus 1/2 and then plus 1/2. So, and if we have a refinement factor of 2, yeah, then this here turns out to be 2, such that we can write this as 1 over omega fine is equal to 2 over omega cos minus 1/2. So this is what you get if you refine one level. Yeah. Obviously, if you refine another level, you would have to apply this recursively. Okay. Now this is how it's done for the last 30 years. Actually, not anymore, but it has been. So volumetric refinement, wrapping up. So what is the good thing? The good thing, it is still, I think it is still almost the only, I mean, there are some, okay, I'm not sure it's the only one, but it is still the method that most obviously conserves mass and momentum. Yeah, so this thing does not lose any mass and momentum, but you have to be aware that you can actually overdo conservation of mass and momentum. Yeah, so I think in the Navier-Stokes equation, yeah, you have control volume methods that conserve mass and momentum usually completely. Then you have finite element methods that also work, and finite elements methods don't care about conservation. Yeah, so they care about solving the equation, they're not about conservation. And this may actually be better. And there are reasons to assume that it may, under certain circumstances can be different, yeah, but it may, under certain circumstances, be better to actually try to solve the equation as good as possible, rather than to strictly just impose the conservation laws. Because imposing conservation laws actually is pretty simple. Yeah, so it's easy to write to make a method that conserves mass and momentum. I mean, in principle, all you have to do is, after each time step, calculating how much mass and momentum you lost, and decide on one point in your domain where you just dump all the mass and momentum that you have lost, so that the mass and momentum stays conserved, right? So that would solve this problem. And I mean, a little bit more clever would be to distribute it somehow, yeah? And if you watch PhD students a lot in these conferences, you will notice that they reinvent this global redistribution algorithms again and again and again. And usually it does not really improve things that much. So reason for this, if you overdo one thing, you underdo something else. Yeah, this is usually the case. Yeah, so actually what you get, and this is surprising, I mean it could be surprising, you get a discontinuity in pressure. In pressure and in stress. Okay, so it's understandable that you get a discontinuity in stress, that you get a discontinuity in pressure when you conserve mass and momentum is actually more difficult to understand. And I think I'm not going to try this now. If anybody has later an interest, we can talk over 2 hours to see why this is the case. But the observation is, and this is one of the disadvantages simply by observation of these methods, is that they generate discontinuities in pressure. So they're actually inconsistent. Yeah, it's not even that they have a kink in the pressure, but they actually have a jump in the pressure. Inconsistent. And the other thing is, so here you can again say this is good or bad. They're highly dissipative. I think this is a good thing in a way. Okay, I mean, this was used. This method is particularly used in commercial codes. Yeah. Now, industry is a little bit different from, I mean, they want to have correct results somewhat, right? But they may not care about too much detail. So what they, I mean, if you think about CFD colors for directors, they want to have a result, right? And then saying that your method is dissipative, so the mathematician would potentially say that this makes it inaccurate, right? But if it's dissipative, it is stable. And this is of course a big problem if you want to, if you are in the late 20th century and you want to simulate the turbulent flow of a car at Reynolds number 6 million, right? You have a stable method, you get a result. That's very important. So if this is good or bad, you decide. So problem mainly being is that this explosion is actually next neighbor interpolation, and next neighbor interpolation is of 0 order. Zero-order interpolation. And let's briefly discuss what kind of interpolation would be necessary to just get a consistent, I mean not necessarily a high order, but a consistent relation in the Navier-Stokes equation. So this is a little bit intuitive. Maybe mathematicians would complain here, but let's think about this in an intuitive way. Yeah, look at the Navier-Stokes equation, which is the thing that we want to solve. Say we solve this here with the Lattice Boltzmann method, and we have rho to the 0 order, I will now write this material derivative. So this is dt u plus nabla uu, yeah, times rho 0, yeah. Together I put this into here because this is not what I want to talk about. What I want to talk about is the right-hand side of this equation, and on the right-hand side we have theta times the gradient of the second order of rho plus the 0 order of rho times viscosity times the Laplace operator on the first order of u, right? So this is what you see in the Navier-Stokes equation, which you're hopefully familiar with. Now, what sort of interpolation, what sort of approximation of our results do we need in order to actually evaluate these terms? Yeah. So if you think about it this way, if you do the explosion algorithms, then the nodes next to each other, they all have the same value, right? So if you take a finite difference, or you calculate the gradient in any different way, you wouldn't see any change there. Yeah. Yeah. You take the first derivative of them, you don't see a change because they are all the same. Yeah. So here for the pressure, so this is basically the pressure here. So what you need is that it is C1 continuous, yeah? That it is at least approximated by a linear function, so that you can actually have of this thing a first derivative. Otherwise, the first derivative would just be 0, right? And this here would be gone. Yeah? So this requires that this is the first derivative and this requires at least linear interpolation. Meaning that the variation of this over space must be at least a linear function, so that when we take the derivative, we get a meaningful gradient. Here for the velocity, we have a second derivative. And the second derivative implies that we need a quadratic interpolation. So obviously, when we do explosion, we don't have this. So now instead of using the volumetric approach, we come to the interpolation methods, of which there are many. And one of the classical examples, also coming out of the 90s, is the interpolation on overlapping grids. Now you notice in the volumetric method, the grid points were not overlapping. And there was an interpretation that is kind of different from the interpretation that we had so far. And in a way, this is also important. So our interpretation was that we have a collocation method with Lattice Boltzmann, yeah, that we have that we measure the macroscopic variables at collision time, which means we have the velocities and the density or the mass on these nodes, right? The interpretation that was used by power flow is that the velocity and the density is the average in that cell. Yeah? So you will find in literature different interpretations and different wordings where people speak about lattice cells and lattice nodes. I don't know how the Krüger book deals with this. Does it say with cells or does it say with nodes? Anybody remember? So I mean, there are two religions, so to speak. Yeah, the one believe in cells and the other one believe in nodes. So important thing is the asymptotic analysis that we did is based on nodes. If you want to interpret your method in terms of cells, then you have to do a different kind of analysis. So however, if you do this different kind of analysis to second order, you get the same result. And because it's a second order method, it's difficult to say that they are right, that we are wrong. So because both up to second order, both interpretations are equivalent. Yeah? So yesterday in the second session, I told you about eliminating the error, yeah, going first order. This was under the interpretation of our asymptotic analysis, so this works for cells. If you want to have a first order lattice Boltzmann method, then you get a different result when you interpret it as cells than when you interpret it as nodes. Yeah? Because in cells, you don't have the value of the flow in this place, but you have an integral over this in a certain surrounding. So now we go back to the interpretation of nodes here. Yeah? So we, when you interpolate, you're not solving an integral and trying to you capture this. You could also do this, but this is not done here. So now we are back in the world of lattice cells, nodes. Lattice nodes, and say we have a coarse grid here. And then we have a fine grid starting from here. So this fine grid has, of course, what am I doing? Okay, I guess this is why it looks so strange. It must be 4. Okay, so they have, say again, they have twice the resolution. And here we have something that we call hanging nodes. So this hanging nodes, they require interpolation in space. The others don't need interpolation in space because you see they would overlap with the coarse grid, right? So, however, they still require something, namely, because we use acoustic scaling, they require interpolation in time, because we don't have synchronous time steps. So, and these nodes, obviously, they don't need any interpolation because they exist on both grids, yeah? Which may be a good thing or a bad thing. Let's see. So, what we need is to have a data transfer between the resolutions, I mean between fine and coarse grids. And in order to get this appropriately done is we split the pre-collision distribution in an equilibrium and non-equilibrium part. So you could say this can always be done Fij is equal to Fij equilibrium plus Fij non-equilibrium. Then we know from Taylor expansion, so this can be done by Taylor expansion alone. Can also use the full asymptotic analysis. Now I make my life simple and I just Taylor expand this. MAB is MAB equilibrium, and this MAB equilibrium is scale invariant. This means it can simply be transferred between the different resolutions minus delta x over omega. Suppose we are in BGK now, dx m a plus 1 and b plus dy m a b plus 1. So usually over bar. Wait. No. Okay, so the pre-collision, okay, so this, it is 1 over omega because it's the pre-collision state and not the over bar that we get out of here. So this is the non-equilibrium part, actually including the omega. And because I just made the Taylor expansion and not an asymptotic expansion, I have to deal with here delta x squared terms in addition to this. So this is the non-equilibrium part, and here we require some scaling. And this can be done for the populations itself by Fi. So the fine one becomes the coarse one in equilibrium without change, plus delta x fine divided by omega fine times omega coarse divided by delta x coarse, the coarse non-equilibrium population, and the other way around, Fij coarse can be Fij fine in equilibrium plus delta x coarse divided by omega coarse times omega fine divided by delta x fine. F fine non-equilibrium. So this is how they can be translated. All of them come here in pre-collision form. So the first methods that used them, that used this kind of interpolation, actually did this on the post-collision part. So this made other people very happy because they could write a paper by saying, oh, we just do it on the pre-collision and so we are so much better. Actually, doing it on the post-collision part has a disadvantage at a certain has a singularity at a certain viscosity that doesn't play a big role because this certain viscosity is very high, so you seldom use them. But anyway, using pre-collision scaling is likely more versatile in that sense, because post-collision scaling has a singularity at omega equals to 1. So this cannot handle this particular case. So now what you have to deal with is the interpolation of these hanging nodes. Okay, trying to draw this again. 3, 4, 6. Here. So here starts the fine grid. Actually, the fine grid starts with this overlap here. And here we have in this position we have these hanging nodes. So these here are hanging nodes, and this here, the other one, are overlapping nodes. So the hanging nodes need some interpolation, and the interpolation that we apply to the hanging nodes is done like this. So we have used the following stencil. We have a hanging node in between two coarse, hanging fine node in between two coarse nodes. And this is not enough. We need to take the next two hanging coarse nodes into consideration. So this is the interpolation stencil. Doing two things, namely we need quadratic interpolation. So quadratic interpolation needs how many points? 3, right? So, but if there is no, we in Lattice Boltzmann, we like our symmetries because everything is nicely symmetric. And there's no way you place 3 points symmetric here, right? So you take another one, so you have 4, and then you can recover second order, and you have it symmetric, right? These two things together. So this is the interpolation stencil required for quadratic interpolation and symmetry. Okay. So the other nodes don't need interpolation, or they apparently don't need interpolation. So the overlapping apparently, okay, I'm nasty writing this here. No. Okay, they need interpolation in time, but they don't need interpolation in space. Which also means that we only have to interpolate from the coarse to the fine. We never have to interpolate from the fine to the coarse, right? Apparently this is the case. No interpolation from fine to coarse. And this, okay, so this was of course originally considered to be an advantage of overlapping crits. Over staggered crits. So staggered crits is the one that was used in the volumetric approach. So do you believe this is true? I mean, when I'm asking such a trick question, then it's probably not, right? Okay, I have a picture here prepared by one of my colleagues, Sebastian Geller. Okay, some time old, 2011. What do we see in this picture? We see there's an object and there are several levels of crit refinement. I can identify, because I'm close enough, there's an interface here, there's an interface here, and there's an interface here, right? And actually there's another interface here which is not very well visible. So, and here is obviously some turbulent flow. Now, you know, most of these methods were invented when there was nothing else than BGK around, and so you could not simulate turbulent flow easily with the Lattice Boltzmann method in the first place. Yeah. Now, we were working on the high fidelity codes, making it more and more stable, more and more accurate. Yeah. And then we actually want to use this for high fidelity simulation and combine this with the classical methods to do the crit refinement. And what we observe here is that in front of the object, where the laminar flow enters this crit region, there you get streak of turbulence. This is like if you know in turbulence you sometimes put a mesh there, right? So that generates turbulence. So this looks like this. Actually, one of the PhD students said this is a good idea because we have the crit built in, we have the crit already inside, but she was not very convincing with this. So how comes this is the case in the first place? Yeah. So I mean this was very annoying to the people doing this, of course, but there is a very simple reason why this doesn't work, and depending on what type of thing you learned in your life, this may be very obvious to you. Yeah. So I get it that most of you are mechanical engineers probably. Yeah. So I learned electrical engineering and semiconductors, and part of this was signal processing. So even an undergraduate student who studied signal processing would immediately tell you, I mean, doesn't need to be a good student, just you know the basics of signal processing, could immediately tell you that this doesn't work from a signal processing point of view. Yeah. So observation here is this is unstable for turbulent flow. It is actually stable for purely laminar flow, but you can't go to turbulent flow with this. So what is the reason? Now, since you did not study signal, or most of you did not study signal processing, I have to give you a short wrap-up of the specific things about signal processing that are here now important. Yeah. So we have to understand the problems of so-called data downsampling. And there is a theorem due to Shannon. By the way, I mean, people didn't learn signal processing. Anybody familiar with Shannon theorem, Nyquist theorem, Whittaker theorem? They're all the same. I mean, this is just different people, pretending that they that they discovered the same thing. Okay, I should say discovered. Let's say Claude Shannon. So Claude Shannon is the one in America. Whittaker is the one in England. Then there is Katalnikov is the Russian. And what else? Yeah, there was so no German participant in this. Okay, let's call it Shannon. So we should just call it the sampling theorem, because this is what it means. The sampling theorem. So this requires data to be band limited at half the sampling frequency. To avoid, so we talked about this, aliasing. Should I say aliasing or aliasing? Aliasing, I should say aliasing, right here. So aliasing. Okay, so aliasing is something that you have heard about, because this makes your music sound bad, right? And the JPEGs ugly, right? So so you have heard about this, and the context in which you hear about this usually is the sampling theorem, yeah. And the theory behind this goes like this. So basically, you have your signal in Fourier space, and here, so this f now is the frequency, not the population or something. It's the frequency of your data, and here you have the Fourier coefficients. So because we are talking about sampling, this means discrete data points. Also, our frequencies are discrete. So I'll now draw it as a line, but this is just for illustration. Actually, they are discrete points. Yeah. So say Okay, I have to be able to split this up, so I need to make it long enough. Okay, let's say for 8. Yes, say this here is your sample. Okay, so this is the sampling frequency at the finest grid that you are using. Would go up to here. Then the half frequency, SF half, the sampling of a fine grid at 1/2 would be here. Now you will notice the following. If you take Fourier coefficients of a signal, then for every frequency you get 2 Fourier coefficients. Yeah, a cosine and a sine coefficient, right? So then this looks a little bit like you are doubling your information. So because for every grid node, or for every node that you have in your signal, or for every time step when it's a time signal, yeah, but you inverse this to the same number of frequencies, and for each frequency you get 2 values, right? So it looks like a doubling of information, which of course cannot be. So what is happening in reality? Say you have this kind of signal, yeah, and of course I'm telling you these are now discrete points actually, but let's say we have this kind of signal. Then what happens at the higher frequency? You get something that's called a mirror image, mirror data. So simply, the spectrum of your signal is mirrored around this half frequency. Yeah. So that's fine as long as this thing goes down here to 0 quickly enough. Now let's say you want to combine this. You want to combine this with a coarser grid. So you do a sampling on a coarser grid. So here is actually FS coarse grid, so half the frequency. So you have this half frequency here. Now assuming you're using the same signal. So what happens? You get a mirror image around here. And now you notice that in this region, the signal is non-zero. Yeah, and I said that we get here mirror image. So this part here is mirrored into this range, but this range is also mirrored into the other range. Now problem is they are not zero. So what will happen? What is happening is that they will overlap. So the image, so they will be now mirrored. I don't draw it very, very beautifully, yeah, but they will be mirrored here, and they will what is actually in this domain, yeah, will be put in between here. And this will be the apparent. This is not the right signal, but this is the apparent signal. With our aliasing problem. So this happens if you undersample your signal. Yeah? So this means that something that should be actually high frequency, but what does not fit into your sampling will turn out to be of low frequency. So this happens. Okay, let us write this down. This is a Fourier transform of discrete data points. Okay, and FSF is sampling frequency on the fine grids, and FSC is the sampling frequency on the coarse grids. So now this sampling produces this spurious mirror image at Fs half, meaning that the signal at frequencies larger than half the sampling frequency cannot be distinguished from lower frequencies. Distinguished. And this means you would actually require a low-pass filter. Before you sample. And this is also the way this can be done and has been done successfully in the lattice Boltzmann method, grid refinement. So now you may also understand why this problem originally did not show up in laminar flows, because laminar flows often don't contain very high frequencies. Yeah. So, but I mean, this is the problem with this is that also in these flows you don't really need a lot of grid refinement usually. So basically you can work only with this grids if you're with this type of grid refinement if your flow is well resolved on the coarse grid. Yeah, if it's well resolved on the coarse grid, so meaning that it has no frequency contribution above half the sampling frequency, then you can do this. Otherwise, it will turn out to give you wrong results. And turbulent flows are usually, yeah, they are also band limited, as you know, but they are band limited only by the Kolmogorov frequency. And this Kolmogorov frequency you would need not only to resolve on the fine grid, but also on the coarse grid. In particular on the coarse grid in order to avoid this aliasing. So what is the Kolmogorov frequency? This is basically 1 over the Kolmogorov length. So I guess I don't need to explain the Kolmogorov length here. So this is the smallest length scale at which we would observe vortices in turbulent flow. So one other observation is that the staggered grids, so this was the one that there was actually the patent on, not for that reason. So they work, staggered grid works without any filter. And the reason for this is that staggering your grid already filters. Yeah? The thing is, if you have a staggered grid, then you don't have any overlap, then you obviously have to interpolate all of them. All the nodes are interpolated on staggered grids. And the interesting thing here is that interpolation is a low-pass filter. So this eliminates automatically these high frequencies. And therefore, whoever used staggered grids in the interpolation did never run into this problem. Yeah, automatically. So you can now ask, did they think about it beforehand, or have they just been lucky? We don't know. But the thing is, you use staggered grids, you don't have this problem. So this implies for us that we want to use staggered grids. However, we want to use interpolation and not the very simple version that with the volumetric, the simple volumetric interpolation or explosion algorithm. And this we do by the compact interpolation method. So compact interpolation. What's our problem? So we have seen for the Navier-Stokes equation, we would need to have a quadratic interpolation, right? So, but quadratic interpolation requires relatively large stencils, and this is always a problem, because large stencils mean a lot of cost and problems at boundary conditions because they have missing neighbors. Yeah? So quadratic interpolation at interfaces requires large stencils. So we don't like large stencils. We want to have small stencils. So how do we get to small stencils? We reduce the stencil size by the results of our asymptotic analysis. You know, mathematical knowledge looks boring, but can be very useful. I think it's Boltzmann. I think this is a quote of Boltzmann saying that there's nothing as practical as a good theory, right? Now, let's look whether we have a good theory. We now talk about interpolation cells again, and I'm not doing this properly. To use 4. So in this type of compact interpolation, we also use cells. Now, there's something very important to keep in mind, that we understand cells completely different from how the volumetric method interprets cells. So the volumetric interpretation of a cell is this, the node is in the center, and we put something that crystallographic people call the Wigner-Seitz cell. Did you hear about this? No. Okay. So we put the smallest volume around the node that actually would fill then the volume, right? The entire space. So, and this is the volume associated with that node. In these interpolation cells, the interpretation is different. We have, because our interpretation is not that we have the average over a volume, but we have a collocation method where we have the value at a certain point. Meaning that in this cell, we put the nodes at the corners, yeah, not in the center. So, and so this here is an interpolation cell. And this interpolation cell is used to recover, say, for example, a finer resolution. So this would be here coarse to fine interpolation cell. And we can have also the opposite, a smaller cell. Okay, let's draw this with circles. And this would be a fine to coarse interpolation cell. So, and here we call these round things here, these are the source nodes, and the pluses here, they are the destination nodes. So information that we are using for the interpolation in order to be consistent so the information at the source is, of course, we interpolate rho, we interpolate u, and we interpolate v. But this is not enough to obtain second order interpolation, yeah? Because there are not enough points here. So we add this, we pop this up, we don't pop it, we increase the amount of information by using the moment m11 and the moment m20 minus m02. Of course, this is now in 2 dimensions. Yeah. Then, according to our asymptotic analysis, we can write m11 to second order minus m11 to second order equilibrium divided by rho actually to, wait, rho 0 is minus 1 over omega, so there's a pre-collision, yeah, pre-collision states. A minus 1 over omega theta dx v1 plus dy u1. And also the others, m20 to second order minus m02 to second order minus m20 equilibrium second order. I should have written this here more beautifully like this. Plus m02 equilibrium to second order divided by rho 0 is minus 2 divided by omega times theta dx u to first order plus minus dy dyv to first order. So we know the velocities and we know their spatial derivatives. Yeah? So with the spatial derivatives, we can increase the order of the interpolation that we use. So say we make an ansatz for second order interpolation. Functions. So in saying that we want to recover u in x and y, yeah? And we make a polynomial interpolation. So this is, we're writing down a polynomial saying that this starts with a zero constant part, then with ax times x plus a y times y plus ax y times x y. So this here would be a bilinear interpolation. Yeah. So this is 1, 2, 3, 4 terms that we could recover given the 4 velocities on the 4 edges, no, not edges, corners of the interpolation self. And this is not enough because it's not fully second order. So in order to get it fully second order, we have to add ax x square plus a y square. So similarly for we have x, y equal to b0 plus bx, x plus b, y plus b, xy times xy. And this is what we could do without any further information, but then what we actually need is bxx square plus y square. So, and say for the density rho, we need only first order interpolation. So we'll stick here with this just using the bilinear, what is this? The bilinear interpolation x and y. So this is bilinear. So this can be done without further information on the gradients of rho. Okay, now let us do some counting. We have 4 nodes times 4 velocity moments, the velocity itself, and twice two times derivatives gives 16 moments for velocity on 4 nodes. However, we need 1, 2, 3, 4, 5, 6 times 2, 12. But we have only 12 coefficients. This means we have an over-specified system. Actually, we have too much information to deal with. So now we have to kind of reduce this. And this is done in the following way. With a data reduction. With finite differences. The differencing stencil. And the stencil looks like this. So we have plus, 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 minus minus, and we call this d. Okay, so we take, we have 4 points, we add 2 of them together and we subtract 2 of them, right? And the location where we compute this derivative is of course in the center between the 2. Now this here would be a normal finite difference stencil for a point here, and the other one would be a normal finite difference stencil for this point here. When we take the average of the 2, we would have an approximation of the finite difference in the center. Then we call this the dy of something, and then we also have the dx of something. And now we apply this to the M11. Namely, we do dx. So now what is in M11 is dxv plus dyu, dyu. And if we now take the derivatives, if we now take this derivatives of this polynomial, what is left is 2bxx, So this 2bxx, this basically comes from here. So because we are taking the x derivative, no, this comes from this here. So we take the x derivative from here and another x derivative from here of this. This gives us a 2bxx twice the, and then we have dx dy on u. This is plus axy. And if we take the other one, if dxv plus dy u, and this gives us bxy plus 2ayy. And we apply the same thing to m20 minus m02. Here we get to dxu minus dy is equal to 2axx minus bxy, and the same in the other direction. Is axy minus 2byy. So now we reduced these 4 data points in such a way that that now we can solve the equations for the coefficients. So all the other coefficients from velocity at the nodes. And now we solve this. We solve the system for the coefficients. This can, of course, be done once and you have them. Looks a little bit ugly in 3 dimensions. Then what we do is we apply these in the interpolation. For the moments, and what we still have to do is we have to recover the non-equilibrium part. So how do we get the non-equilibrium? So we need to have the equilibrium part. So we calculate the velocity. Then we take the velocity squared, because this is what happens in the equilibrium part. There we have velocity squared. And then we also need the non-equilibrium part. And the non-equilibrium part contains these derivatives of u, and the derivatives of u we get by taking the same derivatives of this interpolation function, and evaluate them. So get non-equilibrium populations from the derivatives of the interpolation function. The interpolation functions. Okay, so this leads us at last to the algorithm that we are using. Okay, for this algorithm, I have to draw again a grid. This, say we have a fine grid on the left side now, because I think I've always drawn the fine grid on the right side before. Okay, but now in order for me to be, okay, let's have the fine grid here, and then, yeah. Have a fine grid here. And say we put one interpolation cell to this and the next interpolation cell to this here, and maybe I'll make it a little bit shorter because we don't need these. So then goes the fine grids on, and we would have the next coarse grid cell, we would have them here, and 1, 2, 3, 4 on, and here. And say we put these guys here. So now how would we put our cells? Now from here, so this is obviously fine, and from here we only have coarse, and say we have this overlap. We have this overlapping system like this. Yeah? So where these here are the fine cells on the left side for interpolation, and we have shown here one coarse on the right side, and this of course would now go on like this. So now assume we have here step number 1. All nodes have known values. Also, all nodes are known. All populations on the nodes are known. Now let me be a little lazy now. I know you have it more difficult, but I'm going to I'm trying to, okay, I'm not able to. So I'm trying to copy this, and then I'm pasting my same grid here for the next step, for step number 2. So we do step 2. In this step 2, we do a fine time step. So remember, we have acoustic scaling, so we have 2 fine time steps during one coarse fine step. So one fine time step means, because these fine nodes here, they don't have any neighbors on their right side, right? They don't have any neighbors, so there's no streaming to them, so they become invalid in this time step. So we have to forget about them, bless you. So this thing is followed by another fine time step, because there are 2 of them. So this is, say, step 3. There's the second fine time step. So the second fine time step means, so they are already gone, right? So when they are gone in the previous time step, then these here have after this time step no more neighbor. So they become invalids too. So now we've lost all these nodes here, and we'll follow this up by one coarse time step. So this is now step number, what am I doing? Step 4. Here we do a coarse time step. So one coarse time step per 2 fine time steps. Meaning collision and streaming, right? So collision, so these guys here are already gone. So and then we do collision and streaming on the coarse grid, and because after streaming they don't have any neighbors on their left side, they will be gone. People are starting to take pictures because it's too difficult to draw this, right? Yeah. Okay. So now everything that has been interpolated before is gone, but now we have done 2 time steps on the fine grid and 1 time step on the coarse grid. So now this fine and coarse, they are now again synchronous. Yeah, this is time for synchronizing them. And this is the 5th and last step here. So we have step number 5. Maybe I write it like this. Do you see the others? So step 5, this is synchronization. So we do synchronization. That means we have the interpolation. We interpolate at all interfaces. Meaning, let me use this now. We recover these nodes here, yeah, from interpolation, and also these nodes here again from interpolation, all at the same time. So after this, all the nodes are again known, and we can return to step number 1 and go on. So doing these things, doing it this way, with the overlap, has the property, which we think is an advantage, that we do not need any interpolation in time. No interpolation in time is required. And also, no special treatment for corners and edges, which is different to other interpolation methods. Okay, now this in principle now concludes the lecture on grid refinement. Yeah, we'll we'll have a break and later see again how this is done in practice in virtual fluids. So now there has been a question with regard to forces. Yeah, because I was not explaining anything about forces in this lecture, and somebody wanted to have me talking a little bit about forces. So what we could do is I could spontaneously tell you something about forces, and I could, for example, do this now, or we'll do it after some break.